So recently we had big maths news, didn't we? We had that new prime number that was found, and it was the biggest prime number ever found. And it was big news, and we were all quite excited about it. It was lots of fun. But it got me thinking about one of the classic proofs in mathematics, and that is the proof that there are infinitely many primes. So even though we found this huge 17 million digit prime number, it is still not the biggest prime number of all, because there's infinitely many of them. So shall we do this classic proof? So I'll say before I start that many of you may have seen this proof before. It goes way back, but for those who haven't seen it before, this is what mathematicians consider an elegant and a beautiful proof. So we're going to prove infinitely many primes. To do that, first of all, we're going to assume the opposite. So I'm going to say there are finitely many primes. So if there's finitely many of them, we can write a list. And let's do that. I'm going to call them prime 1. Don't know what it is particularly, but let's call it prime 1, prime 2, prime 3, and I'll just go on until I get to the last one, which I'll call prime n. The point I want to make, though, is that this is a complete list, so that's important. Okay, the next thing I'm going to do, I'm going to make a new number. It's a whole number. I'm going to call it q. So let's call it q. And to make this number, I'm going to multiply all these together. Prime 1 times prime 2 times prime 3, all the way up to the last one there, prime n. So there'll be only one way to write q. As a product of primes, it's a unique expression. So there's only one way you can write q. And then I'm going to add 1. Q is either prime or it's not. That's the only options it has. If q is prime, then it's a new prime that's not on this list. That's bad. So hopefully it's not a prime. If it's not a prime, then it is made up from primes by multiplying primes together. Now those prime factors of q will divide q exactly. And here's the problem. None of these primes on my list divide q exactly. They'll divide this number perfectly, but not this +1 number. You'll always have 1 left over. So the prime factors are not on this list. So this list is not complete. I said if there's finitely many of them, I can have a complete list. You cannot. And that's the proof that there are infinitely many primes. So the definition of a prime is that it's the building blocks of other numbers. So all other whole numbers are made by multiplying primes together. So q is a whole number, and it is made by multiplying primes together. And in this case, the problem is none of the primes on my list do that trick. They don't divide the number exactly. So there's primes missing. What I've got here is a copy of a book called Euclid's Elements, and this is a textbook written by a Greek mathematician called Euclid. Now Euclid lived in 300 BC, so this textbook is 2,300 years old. It's never been out of print, and it's second only to the Bible in that respect. It's one of the most important books in mathematics. It's one of the most important books in human history, and the proof that there are infinitely many primes is in here, and I checked it out earlier. It was on page 227, which is book 9, proposition 20, and it is right there, the proof that there are infinitely many primes. There's a couple of differences from this proof to what I did. One difference is my proof there was something called a proof by contradiction. It's something that mathematicians do a lot. It's really useful. What Euclid did was slightly different. He assumed that there was a list of primes, and he said, but you can keep adding to it, so you can never complete the list, which is the same sort of idea. The other difference is that this book was written in the days before algebra. So he didn't have algebra to use like I did. So all his proofs are using straight lines and circles. So it looks quite different, but it's actually quite easy to translate into modern terms. You see, mathematics is the search for truth, and this book is as true today as it was 2,300 years ago. We know a prime number can only be divided by 1 and itself by no other factors. So how did Euclid define it? It's actually in here. I was quite excited when I found this. So let's have a look. In definitions, look here at the beginning of book 7, he defines terms. Look at that. A prime number is that which is measured by a unit alone. So only units fit into the prime number. It was all measured with lines. So the length of a line with length, a prime, can only fit units into it. You can't fit 2s and 3s and other lengths into it. So if we had something that was prime length, let's make it 7. There we go. Then you can fit 1s into it. 2, 3, 4, 5, 6, 7. But you wouldn't be able to fit 2s into it. So here's a 2, and that would not fit into my length 7. Or if I tried, 4s or 3s, it wouldn't fit into my length 7. So a prime length would only fit units into it and itself, and that's the definition of primes we have today.
So what does that mean for that new prime number that was found?
It's tiny. That new prime number, 17 million digits long, tiny, nothing, insignificant. To the whole infinity of prime numbers, it is small fry.
My understanding is that prime numbers become less frequent the higher you go. Their density becomes lower. Does that mean the next prime number is likely to be a long way away from those 17 million digits?
They become more spaced out. You are right about that. And there's, we're getting into other things here, but there are some fantastic theories or theorems about how the prime numbers are spaced out, the density of prime numbers, but we are slipping into other realms there.
Sounds like another video.
It does sound like another video. It'll be a good one as well.